morning everyone. My name is Mrudula, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. Today I am going to discuss a topic called Power Factor Correction from the subject Industrial Electrical Systems. These are the topics which I am going to discuss today, like AC power, inductive loads, capacitive loads, what is power factor, and what is the power factor triangle, the causes of power factor and how it can be corrected. AC power. What is an AC power? In AC power, we will be dealing with three different types of powers. That is active power, reactive power as well as apparent power. So in AC power, we will be having three types, that is active, reactive as well as apparent. What is active power? Active power is which provides the working part of the power systems. That means which provides the heat, light or motion. Reactive power. What is reactive power? Reactive power is which maintains the electromagnetic field, and provides no working part, for the power systems. Apparent power. What is apparent power? Apparent power is provided both working as well as non-working parts of the power system. That means nothing is apparent power is equal to active plus reactive power. Apparent power you will be measuring in kVA. Active power you will be measuring in kilowatt. Reactive you will be measuring in kVAR. That means kilovolt ampere reactance. This is kilovolt ampere. This is kilowatt. This is kilovolt ampere reactance. Here this active power you will also call as real power. The active power you will also call as real power, means the power which is really used, for lighting or for heating or for movement of any object. So the real power is the active power. The reactive power is occurred because of the inductive as well as capacitive loads or the changes which are being caused in the different types of loads which are being connected to the bus bars. So because of loads, the reactive power comes into existence. The combination of both active as well as reactive power is nothing but the apparent power. So these are the three different types of powers which are being occurred in the AC powers. Here you can see the waveform. In this waveform, the x-axis is nothing but the time. And the y-axis shows us the energy. That energy, here you can see energy stored, energy released, energy stored as well as energy released. That means for this waveform from 0 to T1, that is this one, 0 to T1, voltage and current both are positive and therefore power is positive, because power formula is P is equal to voltage into current. So as voltage and current both are positive, the power is positive. And at T1, at T is equal to T1, voltage V is 0. Here you can see this is the picture of power. This black dot is the picture of current and this is the picture of voltage. That means colorful picture is power, dotted line is current, dark line is voltage. So from 0 to T1, voltage and current are positive. The current as well as voltage both are positive. So the power is positive. From T1, at particular point T1, in this point voltage is equal to 0, current is equal to positive. So at T is equal to 0, voltage is equal to 0 and thus power is equal to 0 because P is equal to voltage into current. So power is equal to 0 at this particular point T1. And now from T1 to T2, from T1 to T2, you can see from this particular T1 to T2, the current is positive, current is positive, current is positive, voltage is negative. So the power, that is V into I, is negative. Next one, I is positive, voltage is negative, therefore P is negative. From T2 to T3, that means from this part to this part, from T2 to T3, you can see current is equal to negative, voltage is also negative. So power is equal to V into I, that becomes positive. When both voltage and current are negative, the power becomes positive. So here you can see the positive picture of the power. So therefore the power is positive and so on. So based on the voltage and the current values, the power will be varying from the positive picture to the negative picture. So when the power is in the positive stage, you will call it as energy stored. And when the power is in the negative cycle, you will call it as energy released. In this picture, you can see the energy stored is more when compared to the energy released. So the positive value of the power waveform represents the real or the working power. The positive power, that is this point. The positive point shows you the real or the working power. Then which delivers from the source to the load. That means from this is your source, this is your load. So from source to load, how much amount of power is being delivered is nothing but your real or working power. The negative value of power represents the reactive power. The negative power, this means this one, this part. This part represents the reactive power. That means the power which is returned from the load to the source. That is from load to the source which is being returned. That power is nothing but your reactive power. So in this picture you can see the active power as well as reactive power. AC powers as well as power comparisons. Here you can see different types of loads. The first one is the resistive load or a heat load. Resistive load which provides a heat. This second picture, this is resistive load. This one is inductive load. This one is capacitive load. In resistive load, the voltage and current are under same phase. That means there is no phase difference between voltage and current. In this picture you can see this is your voltage and the current is also same. The current waveform is also similar to the voltage waveform. That means the cutoff points are same. There is no phase difference between there is no voltage is also starting point is 0, ending point is 360. Ending point is 360. Current also starting point is 0 and the ending point for the first cycle is 360. So, the power, the combination, power is the combination of voltage into current, that is also in the same phase. So, here the power, voltage and current, all three are under the same phase without any phase difference. This is for the case of resistive load, pure resistive load. The second picture will show you the inductive load. In inductive load, here you can see the current is starting from 0. Here you can see the current is starting from 0, but voltage is not starting from 0. It has a maximum peak here. So, at this particular point, current value is there, voltage is 0. And again, at this particular point, the current is 0, but voltage is present. So, at this particular point and at this particular point, and let us take this particular point. At this particular point, again voltage is there, current is negative. At this point, current is 0, voltage is negative. At this point, current is positive, voltage is 0. So, there is some kind of phase difference between the voltage as well as current. So, the power also is not in phase with the voltage as well as current. In the third picture, in the capacitive load, also you can see at this particular point, voltage is 0, current is present. At this particular point, current is 0, voltage is positive. At this particular point, voltage is 0, current is negative. So, here also there is a phase difference between the voltage as well as current. So, from these three pictures, we come to know that there is always a phase difference between the voltage and current for inductive as well as capacitive loads. There is no phase difference in an inductive load or for a heat load. See, the electrical energy is almost exclusively generated, transmitted and distributed in the form of alternating current, that is in the form of AC. So, therefore, the question of power factor comes immediately into the picture because it is an AC transmission as well as distribution. The most of the loads, 80% of the electrical distribution system are inductive. Most of the loads are inductive in nature and hence they have a low power factor which is highly undesirable. Okay. So, for AC, when AC comes into the picture, if it is resistive load, there is no power factor difference. But if at an inductive load, the power factor is low. For capacitive load, it is high. Because there is a phase difference in these two, there is a phase difference between voltage as well as current. Low power factor causes increase in reactive current, resulting in additional losses of active power. That means, if power factor is low, what will happen? Reactive current increases. Reactive current increases. When the reactive current increases, in this picture I have shown you, active means, active means from source to the load, reactive means the power which is going back from load to the source. So, we need more active power, less reactive power. So, for good efficiency of a system, we need more active power and less reactive power. But here in this picture, when most of the loads are inductive loads. What is happening? The reactive power is increasing when compared to the active power. So, when the reactive power is increasing, the overall efficiency of the system reduces and the power factor also varies. So, the power factor causes an increase in the reactive current, which results in the increase in the reactive power also. Next, it is important that power factor as close to unity as possible. That means power factor should be almost equal to unity. Unity means 1. If the power factor is almost equal to 1, we will say that efficiency of a particular system is very good. So, we always try to make the power factor to be equal to 1. It will be never equal to 1, but we will always try to make the power factor to be equal to 1. In this picture, you can see this is the voltage, this is the current. So, here you can see the voltage is starting at 0. The voltage is starting at 0 and the current waveform is starting at a particular point theta. Voltage is starting at 0, current is starting at a particular voltage 0 degrees, theta degrees. So, the phase difference between voltage and current is nothing but theta. The phase difference between the voltage and current is nothing but the theta. That means we can say it is lagging. The current is lagging voltage. Current lags behind the voltage, which is for the case of inductive load or for RL load. For L load or for RL load, the current lags voltage. Current lags voltage. We will call it as lagging. And in this picture, you can see here we have connected a capacitive load, that is RC load, resistive as well as capacitive load. The voltage is starting at 0 degrees, but the current is starting at minus theta degrees. Means before voltage only the current is starting. That means you will call it as current leads voltage. You will call it as current is leading the voltage. In capacitive load, in inductive load, we will call it as lagging. In capacitive load, we will call it as leading factor. Okay. So, the power factor is lagging here and the power factor is leading for the capacitive loads. In this circuit, this is only pure resistive load. In this pure resistive load, there is no phase difference. The voltage is also starting at 0 degrees. Current is also starting at 0 degrees only. So, when both voltage and currents are starting from the 0 degrees only, there is no phase difference and there is no power factor. That is, power factor is nothing but cos theta. Power factor is nothing but cos theta. When there is no phase difference, the power factor is nothing but 1. You can see this is your sine waveform and this is your cosine waveform. So, according to your cosine waveform, cos 0 is nothing but 1. Sine 0 is nothing but 0. So, the power factor is 1 for pure resistive load. For pure resistive load, power factor is equal to 1. We always prefer to have power factor 1 because when power factor is 1, active power is more and reactive power is very less. Means losses are very less. So, here is a power triangle. This is nothing but a power triangle where this is the working power. Working power you can also call it as real power or active power. real power or active power, and this is the apparent power, and this is your reactive power. So the angle between the working power as well as the apparent power is nothing but your angle theta. That is the phase difference between the voltage as well as the current. So when the phase difference between the voltage and the current is 0, what will happen? Apparent power is nothing but the working power itself. There will be no reactive power. When theta is equal to 0, there will be no reactive power. Reactive is equal to 0 and active is equal to apparent, which is mostly preferred. So, the cos phi formula is cos phi or cos theta is nothing but working or real power by apparent power. Cos theta is nothing but working power by apparent power. That means working power you will measure in kilowatts, apparent power you will measure in kVA. So the ratio of kilowatt per kVA is nothing but your power factor. Power factor may be defined as the ratio of active power to the apparent power. For leading currents, the power triangle becomes reversed. The power triangle becomes reversed. Okay. So, power factor or power triangle. Here you can see the power triangle. The power factor is equal to cos theta, that is cosine of angle between the voltage and current, and one more formula for the power factor is resistance by, here this is your resistance, this is your reactance, this is your impedance. So the cos theta is nothing but cos theta is equal to resistance by impedance. That is R by Z. Z is nothing but R times of J into X. Z is nothing but R plus J times of X. This X may be XL or XC or combination of X. Yes, there is a small problem. S is equal to VI, S, P, Q. S means kVA, kilowatt, kVAR. kVA is nothing but apparent power. So, for apparent power, we will give the symbol designation as S. Next, kilowatt is active power. Active means P. kVAR means reactive. Reactive means Q. So, here you have S, P and Q. S is apparent, P is active, Q is reactive power. Here they have given 3 values of SP and Q, and the circuit receives an apparent power of 2 kVA and is able to convert only 1.6 kilowatts into the working or the active power. Means out of 2 kVA, only 1.6 kilowatt is being converted. So, the reactive power will be, as I said, apparent is equal to active plus reactive. So, the reactive value will be now. So, the reactive value, see, the active power is nothing but, the active is the power which is flowing from source to the load. The reactive is the power which is being wasted or which is being returned back from load to the source. So, the active should be always more than the reactive. So, here the active is 1.6 and the reactive is 1 point. So there are different types of electrical load, different power factors. Based on the different loads, the power factor differs. See here, lightly loaded inductive motor. Lightly loaded inductive motor. In inductive motor, we will be having an inductor. Inductive component is more. So when the inductive component is more, lagging will be there. So we will be having 0.2 times of lagging. Power factor percent is 0.2%. For fully loaded, it is 0.2. For fully loaded, it is around 0.8 lagging. And for neon lighting equipment, it is around 0.3 to 0.7 lagging. For incandescent lamps, it is heat bulb or like pure resistance. It is like pure resistive load. Here we will be having unity power factor. There will be no lagging, there will be no leading. And for all types of resistive heating devices, example toasters, heaters and all, we will be having one, that is unity power factor. So these are the different power factors for different types of loads. Causes of low power factor. What are the different causes for the low power factor? Most of the motors are induction motors. Either they may be a single phase or a 3-phase. So at a light load or at a heavy load, they are lightly loaded or fully loaded, the power factor varies. As I said in the previous case, even it is lightly loaded, it is 0.2. Even it is heavily loaded or fully loaded, it is 0.8. So based on the load, based on the full load or half load or light load or single phase or 3-phase, the power factor varies. And arc lamps. Second point is arc lamps. Arc lamps, electric discharge lamp, and for welding equipments as well as industrial heating furnaces, they operated at low lagging power factor. They all are operated at low lagging power factor. So for induction motors also it is lagging, and for other heating furnaces also they are lagging. And transformers. Transformer draws a magnetizing current from the supply. Transformer draws a magnetizing current from the supply. At normal load, the current does not affect the power factor, but they draw larger amount of magnetizing currents at light load. When the load is very less, it draws maximum amount of the magnetizing currents, which causes the primary current power factor. Okay. So when the transformer is loaded heavily or loaded at full load, there will be no problem. But when the transformer is connected to a very light load, then the power factor lagging occurs. So here there are different causes for the lower power factors. Demerits of low power factors. So when the power factor is low, what happens? When the power factor is very larger kVA rating. The first one is larger kVA rating. Electrical machines like alternators, transformers, switch gears are always rated at kVA, kilovolt ampere rating. For any kind of equipment varies inversely with the power factor. Therefore, low power factor increase in the kVA rating. As a result, kVA rating of the equipment larger and expensive. That means as the power factor reduces, the kVA rating of the equipment increases. As the kVA rating increases, the cost of the equipment increases. As the kVA rating increases, the cost of the equipment also increases. So, the power factor affects the increase in the equipment and makes them more expensive. The second one is greater conductive size. Greater conductor size. To transmit a fixed amount of power at constant load, at constant voltage, the conductors will have to carry more current at low power factor. That means when the power factor is low, the conductor will have to carry more amount of current. More amount of current. In order to carry more amount of current, the size of the conductors increases. As the size of the conductors increases, the cost of the conductors also increases. So this will increase the size as well as cost of the conductor. It will increase the kVA rating of the equipment, and it will ultimately increase in the cost of the equipment also. So these are the two different factors of low power, demerits of lower power factor. The third point is larger copper losses. The larger the amount of current at low power factor causes I square R losses. Okay. So as the power factor reduces, the I square R losses, copper losses also increases. And poor voltage regulation. The voltage regulation, the larger the amount of current produces, larger voltage drops. In alternators, that is, alternators is nothing but the AC generators. So in AC generators as well as in the transformers, transmission lines and distributions, the voltage regulation is done poorly. So the results will have a poor voltage regulation. Next one is extra utility charges. So as the system power factor reduces, the uneconomical from the supplier's point of view. So it becomes uneconomical with the supplier. As the power factor reduces, the transmission reduces. Transmission reduces, and in order to bear the load, in order to provide proper power to the load, more amount of power should be transmitted from the generating stations. So when more amount of power to be transmitted from the generating stations to the load, because of this low power factor, automatically the cost of transmission as well as the burden on the load also increases, and the operated the load per the low power factor, and extra charges for the customers are, and this increasing the transmission power is nothing but increase in cost, and that cost is being bared by this customer. So as the power factor reduces, the charges which are being provided for consuming to the consumer also increases. Power factor correction. How the power factor can be corrected? The process of supplying the reactive power. That means the process of supplying the reactive power, that is the lagging or the leading, to bring the power factor closer to the unity, is nothing but the power factor correction. As I said, the power factor should be always near to the unity, that is U1. So in order to reduce this lagging or the leading effect, and in order to make the power factor to the unity value, you will call it as power factor correction. And this can be done by using the following equipments, like by using different types of resistors, inductors, capacitors and synchronous condensers. Here you can see power factor correction, that is a static capacitor. By using a static capacitor, you are trying to compensate the power factor. You are making the power factor correction. That is, the capacitor draws a leading current and neutralizes the lagging reactive compensation of the load current, and this raises the power factor. The correct amount of capacitance must be used. That means, see here, resistive loads will have no lagging or leading effect. Inductive load will be having lagging effect. Capacitive load will be having leading effect. So when the capacitive as well as inductive loads are being connected in parallel, here you can see the capacitor as well as inductor, they both are being connected in parallel. So there is a lagging effect as well as leading effect, and the lagging compensates the leading. The lagging compensates the leading. So as the lagging compensates the leading, the power factor will be nearby to the unity. The power factor will be nearby to the unity. But precautions should be taken so that the capacitor value which is being used for compensation must be, you can see, the correct amount of capacitance should be taken. Otherwise, the power factor goes from lagging to the leading, which will cause undesirable condition. That means previously it was lagging. Now because of capacitor, it comes to unity. If the capacitor value is more, it will become into leading effect, and this leading effect may be more worst when compared to the lagging effect. So while connecting a capacitor in parallel to the inductor, we need to calculate the capacitor value properly, and then only we need to connect capacitor in parallel with the inductor in order to reduce the lagging effect and correct the power factor to the unity value. So here you can see, here we have connected an inductor, and this is your capacitor. This is pure inductor and this is pure capacitor. In this, current lags voltage. In this, current leads voltage. Here, assume in this circuit, which is pure resistive load, that is 120 kilowatt, is being connected to a voltage of 600 volts generator with supplying a current of 200 amperes. So S is equal to P is equal to 120 kilowatts. Because it is pure resistive load, there will be no reactive power. There will be the active power. This is your active power. This is your apparent power. Both active and apparent powers are equal, and that is equal to this 120 kilowatts. That is for pure resistive load. In second case, in second picture, a resistor is being connected in parallel to a inductor. That is RL are connected in parallel. So in this case, here you can see the generator is connected to 600 volts and the power factor drops from unity to 0.6. That means previously in this case the power factor was 1 and here the power factor is 0.6. The power factor is nothing but active by apparent. Power factor is nothing but active by apparent. Here this 120, previously this 120 kilowatt is nothing but the active power now, and this is your apparent power. By using this power factor formula, we can calculate this is nothing but the reactive power now. P means active, Q means reactive, S means apparent. This is being measured in kilowatt. This is being measured in kVAR. This is being measured in kVA. So here this is reactive power, so it is measured in kVAR. This is active, so it is measured in kilowatt. In this picture again the same picture, that is R and L are connected in parallel. So you will be having active power as well as reactive power both. And in the third picture you will be having here capacitor. Here a capacitor is being connected here. So here here also you'll be having power factor will not be equal to 1. So now you are understanding that a value of capacitor which is being placed in parallel with the load. Previously only R and L were connected in parallel. Now to this a capacitor is also connected in parallel to the load in order to reduce the reactive power. In order to reduce the reactive power. So this is the formula for the QC value, that is the capacitor value. For calculating the capacitor value, that is voltage square by XC. Here XC is equal to V square by QC. So here we have learnt about different types of powers, that is active power, reactive power, apparent power, and what is power factor and how to correct this power factor. All these things we have learnt. In next lecture, I would like to discuss about kVAR calculations, that is kilovolt ampere reactance calculations. Thank you.